Welcome back to ECE 340 on a brisk morning. Actually, it's afternoon, isn't it? What time is it? 12:30. Yes, it's afternoon. Day 2. Your passport is due this evening. Try to submit that by 11:59. That won't close the Dropbox. There's not any real rush, but I just thought it's best to have some date in mind for you to shoot for, and that's probably getting that done before all your other assignments are due is a good thing. Watch for homework number 1 on D2L. It's going to be due a week from Thursday. I haven't yet submitted it, but homework 1 hopefully will be posted shortly. And some people are asking about reading, what, when, how much, and I'm actually being a little bit vague on that intentionally because you will need to figure that out at some point in future classes or beyond graduation. How do I space my time, or how do I allocate my time? You can go to the syllabus, look at what we are supposed to be covering in terms of the course outline. We are right now assuming you have the background from Appendix B. That's the mathematical background material. You should probably finish that up this week, and we'll be moving into Chapter 1 on Thursday officially. And you can start reading Chapter 1 tonight or Wednesday or whenever. But homework number 1 will include material from Chapter B, the background chapter, and Chapter 1. And it will be dealing mostly with signals, the input and the output. Today what I want to talk about actually is this system so that you see where we're going, what are we trying to drive, what are we trying to manipulate, and really connect with something that you've already done or you should be able to do. And here is an example, and we'll just play with this example just as an illustration. It's an RLC circuit. That's what you should be able to model in this class, and we'll model that many, many different ways. But the general idea is maybe you're given some input, X of t, in this case it's a voltage source, and you want to find what's the output. And the output, which in the textbook is called Y, could be a voltage, it could be a current, somewhere in the system. In this case, I've simply made it the voltage with the appropriate polarity across resistor 2. The idea now is somebody might hand you an input waveform, X of t. It could be a pulse, it could be a sinusoid, it could be a damped exponential, it could be an exponentially damped sine wave. It could be a periodic waveform, it could be an aperiodic waveform. And you want to know what's going to happen at the output Y of t. What's Y of t going to look like across that resistor, the voltage across that resistor? How would you start this problem? Think how you might solve this particular problem. Spend a minute thinking about how you're going to formulate this or set this up. How are you going to find Y of t if somebody gives you X of t? Is everybody hearing all these ideas or thoughts? We're a team. We're trying to work together. There's many different ways of doing this. I heard somebody say an impedance, and I really didn't hear anything after that. My hearing is not the best, so I will have to be more direct in looking and watching students as they respond. How many people would, which domain are you going to go into? I'm asking here X of t is going to be a time domain waveform. Y of t, I want that in the time domain. How were you thinking of solving this problem? Somebody say current loops. Mesh analysis, is that what you're thinking? This is begging mesh analysis, isn't it? It has these two windows, or it has these two meshes. It's saying, oh, you need to be mesh analysis probably. And you could do this with mesh analysis. Where you might say, oh, here's I1, and here is I sub 2. Neither of those two are what you want, though, are they? But you could pretty easily, if you know I sub 2, obtain Y. Y is just that resistor R sub 2 times I sub 2. So if you can find I sub 2, you would be okay. And this is maybe how you would start. But even before you start, and what I want you to start developing in this class is a way to know the answer in the back of the book without the book giving you the answer in the back of the book. Maybe having an idea as to what the answer in the back of the book is before you work through the solution, or at least where am I headed? What might I expect out of this system? In terms of what I might expect, how complicated is this going to be? For example, what's the order of this system or circuit? Do you know what I mean by order? The order is related to the denominator polynomial in a transfer function, and if you don't have any cancellations, generically the order is going to be the number of energy storage devices or elements you have in this circuit. How many energy storage devices do you have in this circuit? So this circuit is second order. It has two energy storage devices. An inductor and a capacitor. Now, if you couldn't think how you might solve this or even how to get started, what's a strategy? Okay, so now you could put everything into the S-domain equivalent, I think was the answer. Find the impedances of everything. What if you didn't even remember that? If you now look at this and go, oh man, I don't really even know how to start, well, you might just change it and work an easier problem. Work a problem that you can solve. For example, maybe you replace these energy storage elements with resistors and say, could I solve that problem? If it was just resistors, I want to get some confidence. I want to build up my confidence so that I can attack this problem. Because then if you can solve that, now you can replace those resistors with these generalized impedances and do the same analysis. And then you're going, oh, now I know what's going on. Let's ask some other questions. What happens to this circuit at low frequencies? How does this circuit behave at low frequencies? So if we're thinking about those impedances, the answer was your inductor is going to be a short because its impedance in the S domain is SL. At low frequency, at DC, the extreme, S is equal to 0. So it has 0 impedance, doesn't it, that inductor? It looks like a wire. At DC, this inductor looks like a short circuit. This is 1 over SC, the capacitor. You make S go to 0, that's going to infinity. This now opens up, and that's not there. You could effectively erase it. So at low frequencies, or at DC, at the extreme, your circuit now looks something like this. It now looks like here is X, here's R1, here is R2, and this is Y. And now we simply have, if everything's DC, this is just a voltage divider. So we just have some fractional relationship between the input and the output. Y is now R sub 2 over R sub 1 plus R sub 2 by times some constant input X. Depending on the ratio of these resistors or the relationship of those resistors at DC, we now, if somebody gives you a constant X, that's what DC is. If they give you some constant input X, you know that Y is just some fraction of that. By this intuitive idea of how these energy storage elements simplify at this extreme frequency. What happens at the other case? What happens at high frequencies? Now I need your help. What's going to happen now? The R's are the same, right? They're not frequency dependent. And the source, X, is going to be some high frequency signal. But now we have to think back at our generalized impedance. We have the capacitor. Is this 1 over SC, and the inductor is SL. Is that right? Now, as we let S go to infinity for high frequencies, this starts to get very small, doesn't it? This goes away. This becomes zero impedance. And what's zero impedance? That's a short. Oh, and we wanted this for our output, didn't we? And what's the impedance of our inductor over here? It's now very, very large, isn't it? Which means that's like we have that air gap. The inductor is like we've now removed that. Now that's become an infinite impedance. This is what we have now at high frequencies in terms of a circuit. What is Y going to be? Well, that's the voltage dropped across R sub 2. That's nothing, right? Because you have no current flowing in that inductor. Its impedance is big. So that now at high frequencies, Y of t is equal to 0. Questions on that? So now this is, that circuit, in a sense, is low pass. It favors low frequencies and it annihilates or gets rid of high frequencies. This circuit now, you could be thinking back in terms of the answer in the back of the book. You might be saying, well, depending on what X is, we sort of know what we should be seeing at the output. If X is of a low frequency, Y will look similar to X. But at high frequencies, we're going to start losing that information or that signal at the output Y. This is now looking like a little bit more complicated low-pass circuit. It's second order. What if we wanted to find a transfer function for this between the input X and the output Y? Because now, okay, we've kind of danced around a little bit. Maybe he'll give me some partial credit. I've told him what's going to happen at DC and what's going to happen at high frequencies. but he wants y given x. So x is anything. It's generic. It's not just DC. It's not just high frequency. So how do we get a transfer function out of this guy? Yes. Okay, so now we're wanting to go into the frequency domain, aren't we? Now we're jumping into the other domain, and we need to get comfortable with that. If we jump into the frequency domain, now we're looking at this S domain equivalent circuit, essentially. We're replacing all of these impedances with their S domain equivalents, and we just wrote those down. The R's are the same. They're R1 and R2. And we'll simply change x of t to, let's say, a capital X of S. And then we want to find what's the relationship, or what's an equation or a set of equations that contain capital X of S and capital Y of S. That's what we want. And somebody said, well, I like to do mesh analysis. Could we do that? So that might be our first thought. Let's now find a transfer function. Do we have to worry about, and we're wanting to find this for non-negative values of time. Do we need to worry about the initial conditions on the inductor and capacitor if we're finding a transfer function? Do you remember how to incorporate initial conditions on inductors and capacitors? This is 320 stuff. I may have a survey. I might have you fill out at some point. I was going to maybe do it in class, but then I thought, oh, maybe I'll just make it on the web. I don't know. But I might start asking you what classes you've had so that I understand where you're coming from. If you've had 320, for example, which is a prerequisite for this class, so my assumption is everybody does. Where was I? Oh, trying to find a transfer function, and I ask, do we need to worry about initial conditions? Can I simply replace everything with their impedance equation or formula and start cranking, turning the crank? So if you take the Laplace transform of these current voltage relationships of inductors and capacitors, the initial condition will come out automatically if you follow the Laplace transform of that derivative or differential relationship. If we want a transfer function, though, luck is on our side. We can neglect initial conditions because now we will get that if we want. But if we simply want the transfer function, we can neglect initial conditions and just find this, let's say, G of S, this model of our circuit. With a transfer function, then, I'm going to just remind us that we can neglect these initial conditions. If that's the case, now let's see, what do I have? I have this source or input. The resistor R1 is not frequency dependent. That's just R1. I have my capacitor, 1 over SC. I have this other resistor, and I have this inductor that has an impedance SL. And now I think everyone is leaning towards mesh analysis. Oh, and I need to find that voltage, Y, with that polarity. Now what am I going to do? I'm going to generically end up with two equations and two unknowns, right? I have two mesh currents, I1 and I2. Oh man, now I have to do some algebra, some linear algebra maybe, some matrices, matrix inversion or Cramer's rule with ratio of determinants. Do I want to do that? So now I start So this is what you might do on an exam, and you're doing this in milliseconds, not minutes, okay? This thought process by the time you get to the exam. But you write this down and you go, okay, I1, I2, I'm going to have to find I2. Well, it's going to be two equations in those two unknowns, and if I can find I2, then I have y of s. Y of s, so if I went this approach, I would have two mesh equations, and then I would have y of s is equal to r sub 2 I sub 2 of s. Well, why don't I just write those down? That's not that hard. Let's just do it. And then we'll come back and maybe solve it another way. Because I said, let's just play with this. Let's find some models of this. Maybe we'll even play in the time domain if we have the time. Pardon the pun, huh? What's the first mesh equation? If I start down here in the lower left, I can simply walk around that. And there are ways of doing this when you don't have dependent sources, but if we just do it the longhand, we can simply say, okay, I'm going into the minus terminal. This is how I would do it. I have minus x of s plus r1 times I sub 1 of s plus, and now I have that capacitor impedance times, and now I want my voltage drop to be positive going from top to bottom. And that means I have I sub 1 minus I sub 2 to get the net current going down from top to bottom to give me my positive. So this is now I sub 1 of s minus I sub 2 of s, whoops, and that's equal to 0. There's my first equation. That's mesh number 1. Questions on that? Now you have a half a point out of 50. Right? We're looking for partial credit. Let's get another half a point by getting the second equation. The second mesh, now, if I start below the capacitor and walk around clockwise again, I have the capacitor's impedance, but now I want my positive voltage to be going from bottom to top, and that means I sub 2 minus I1 will be the net effect going up in the current. I now have 1 over SC. Boy, my writing is... But I write my S's as script S's because if I don't, you might think it's a 5, and then you're going, where did 5C come from? This hopefully tells you that that's the Laplace variable S. That's why I'm doing it in script. You can do it however you want, but that's the reason for my writing or my notation. This is now I sub 2 of S minus I sub 1 of S. That's the voltage drop from bottom to top through or across that capacitor. Now I'm going to the right through R sub 2, and that's just going to be R sub 2 times I sub 2. And finally, I have the impedance of the inductor, SL, times I sub 2 of S, and that's equal to 0. Yes, sir. Well, the way that the question was, how do you decide polarity or the orientation of your voltage relative to the capacitor? And what I'm doing when I write my KVLs, or in this case, a voltage drop on that capacitor, I'm assuming the passive sign convention. And I'm saying I want a drop, I'm saying plus this voltage. And that voltage now, if things work out, if it turns out that I2 is bigger than I1, then it won't be in that polarity. But the polarities will take care of themselves if I'm consistent. So the first mesh, I needed to be having my polarity plus to minus from top to bottom, and that says, okay, then I1 minus I2 is a net current down, And that net current down times 1 over SC is going to be what I need. Then when I was going in the other mesh, it basically flip-flops. It says I want positive to minus now, and now I need I2 is the positive minus I1, and now I have a net current if I2 is bigger than I1 going up, and that will give me this positive voltage drop from bottom to top. Did that answer your question? Now we have two equations and two unknowns. We have an input, x, and our output is nowhere to be found here, but if we know I sub 2, we can calculate our output y. And we could rewrite this if we wanted to. We could collect all of these terms and put it into a matrix. We could now say I have something times I1, something times I sub 2, all equaling my inputs. From the first equation, I have R1 and a 1 over SC all scaling I sub 1. The only thing multiplying I sub 2 is this minus 1 over SC. And if I push the input x or add x to both sides, I end up with my input in the top row of my forcing function on the right-hand side. There's my capital X. And that's now the first equation in matrix form. And I want you to start getting comfortable with matrices in this class, both in the frequency domain and in the time domain. Now I can insert the second row relationship. I look for all of those entries that involve an I sub 1, and there's only one of those, and that will be in the 2, 1 entry of this matrix, this impedance matrix, and that's minus 1 over SC. Then I have all of the coefficients that scale I sub 2, and that will be in the 2, 2 entry. I have a 1 over SC, I have an R sub 2, and I have an SL. And that there's nothing, no input directly adjusting that second, or directly involved in that second mesh. And that's why I have a 0 on the right-hand side. You could have written this down immediately by inspection. You could have said, oh, let me go back to my equation, my circuit, and I would say, okay, the things in the diagonals are those impedances that touch that particular mesh current. In the 1, 1 entry, I find all of the impedances that are touched by I sub 1, and I sum those up, and that's just R1 plus 1 over SC. That's that 1, 1 entry. The 2, 2 entry, I go over to the second mesh, and I say, what are the impedances touched by I sub 2? It's 1 over SC plus R2 plus SL, and that's my 2, 2 entry. Then I say, okay, I need my off-diagonal terms, and I only have 2 mesh currents. Now I look at impedances shared by the 2 meshes. I say, okay, what's the impedance shared by I1 and I2? Oh, that's 1 over SC. Well, that will be in the 1, 2 entry with the negative sign. Then I say, what's the impedance shared with I2 and I1? Well, that's also 1 over SC, and it's a negative sign because it's the sharing. That's now my impedance matrix. And then I look to see what's on the right-hand side or the forcing side, and I say, let me look at my inputs and see if those enhance or make less or impede or deter this positive current. In this case, if I increased X, I1 is going to increase. So X comes into the first equation with a positive sign, and that's the only term on that right-hand side. There are no forcing terms in or inputs in the right-hand mesh, or in the second mesh. So that's why this 0 is there. Questions on where this comes from? Yes? What was the question? Can you type this into your calculator? Over the break, I actually purchased a TI Inspire, but the commands are the same if you have a TI 89, titanium or an 89. It's just laid out a little differently. But this had a nice graphical interface that I could show in class. So now let me go back here and let's clean this up a little bit. What if I make all of my parameters have a value of 1, a numerical value of 1? That will help clean things up. Meaning, suppose that I now say, oh, let's let R1 equal R2 equal 1. Let's let C equal 1, and let's let L equal 1. Now my equations become 1 plus 1 over S, minus 1 over S, minus 1 over S, 1 over S plus 1 plus S, times I1, whoa, uh-oh. Oh, boy. I knew that I was probably pushing the envelope. Yep. Let's. I guess it wanted to change color, so I will let it. I'm not going to object. And now if I want, I can now invert this matrix and invert the matrix, and I will have I sub 1 and I sub 2 as a function of S. Meaning, if I now want I1 of S and I sub 2 of S, that's going to be this matrix. 1 plus, oh boy, this is going to, I was going to really show you what this looks like on, and it forgot everything that I was writing, didn't it? So let me come back, and I now have I1 of S, I sub 2 of S. That's why you can't do this on the exam. Just teasing. But you can't use a computer on the exam. Oh. Okay, that's... So this is now the inverse. Yeah, I can't record the chalkboard. That's why I'm trying to... I know. I've crashed a chalkboard many a time. Here we are. So this is now what we have, and we can, if the computer will cooperate, we can actually put that into the calculator. We can say symbolically, okay, let me put in a matrix. So there, whoops, that's not what I wanted. I just want a square bracket. I can say, what was the first entry? That was 1 plus 1 over S. And that's my first, that's my 1, 1. So I'll follow that with a comma. My next one was minus 1 over S, wasn't it? And that now needs to be a semicolon. That's my first row of my matrix, symbolically, in the TI calculator. My second row is minus 1 over S, comma, there's my 2, 1 entry. And then I had 1 over S plus 1 plus S. And that's really it. That's my 2 by 2 matrix, my impedance matrix. And what I wanted to do was invert that. So I'll raise that to the minus 1 power. And if you're following along, you can see what keystrokes to make, but the TI-89 is a little different. It's maybe even easier, but the S is a little more hidden, so I might use an X instead of the S on the TI-89, but just then do the mapping once you get the result back. Now I want to multiply that by that 2 by 1 input vector. Let me now go down from the exponent and say times, and put in another matrix, and this matrix, and this is a nice thing for having the S's and the X. Let me just call that X. That's just another unknown. That was my input. That will be whatever it needs to be. Then that's the first row. That's my system. That's my circuit. That's my electrical circuit. The transfer line right here. And for those that are watching the video, you'll think I'm crazy. This red line is on the screen. Somebody has marked on the screen with a red marker. I didn't. I really didn't. Question. For the exam, would I recommend? Not necessarily. We're going to work this another way. You can just think through the problem more strategically. This would be a brute force solution. So I'm hoping that the exams are written in such a way that you can be successful without a TI-89. But if you have one, you might as well learn how to use it, is what I'm sort of saying. So if you spend that much money for a calculator, you might as well use it for something other than adding and subtracting. Because we know how to inverse Laplace transform. Meaning, if we now wanted to find a differential equation relationship, if we wanted something in the time domain, we would now be able to say, oh, in the time domain, with respect to time. So this now, this s squared times y, that says, oh, that's two derivatives, or the second derivative of y with respect to time. This now says that a time domain relationship between the input x of t and the output y of t is now y double prime of t plus 2y prime of t plus 2y of t is equal to x of t. And if you like differential equations, now here is a model of your system. This is a circuit model, or this is a mathematical model of your circuit. You now have a power of s in the denominator, the highest power of s in the denominator. Other questions? I'm playing with, and we could find this another way too. We could find, we'll see, we could write two first-order differential equations that are coupled, and they would be equivalent to this second-order differential equation. Let's do this another way, though, to maybe place these people without the TI-89 on similar footing in terms of analyzing this circuit. Maybe they don't want to solve this circuit with a system that involves two unknowns. Pardon? You could do a current divider, you could do a Thevenin equivalent. What I was going to suggest is, why don't we do something that I don't know, it just doesn't come naturally the first few times you play with circuits, but node voltage analysis, nodal analysis. That will actually give us really just one unknown, and that might be now if we just have one unknown, we just have one equation. We can just multiply and divide to get the answer without doing a matrix problem. Now what I want to do is the following. Let me go ahead and redraw this circuit. Let me just say nodal analysis. And now what I want to do, I have exactly the same circuit. It's just now, if I concentrate on that particular, finding the voltage at this node, then I can actually find, using a voltage divider relationship, the voltage dropped across R sub 2. If I know this voltage, then that's just split between R sub 2 and SL, and I can do a voltage divider. Meaning if I can just find this node voltage, I'm basically finished. So let me call this, I'll just call it V sub A, so we don't get all these C's mixed up. But that's basically, with this reference node down at the bottom, that's my capacitor voltage in the frequency domain. If this is now the voltage V sub A that I'm trying to solve for, that's now my unknown. That's my only unknown, V sub A. Let me now try to find an equation, and I can just write KCL at that node to find the one equation in terms of this one unknown, capital V sub A. If I'm doing node volt or KCL, then I need this current, I need this current, and I need this current. And again, I'm working in the frequency domain. To obtain this current going from right to left on the top, or the current through R sub 1, that's simply, so now I'm writing a KCL. That's now V sub A, and this is all arguments of S. I'm going to suppress that for now. Minus X, that's the voltage dropped across R1 divided by R sub 1. That's the current going from right to left in that top R sub 1 branch. The current going down from V sub A down to the reference node, what's that? VA divided by the impedance in that branch, and that impedance is 1 over S, or I'm sorry, 1 over SC. Or, well, I'll just write it that way for now. It's now plus V sub A over 1 over SC. That SC is going to pop upstairs, but right now that's the way I'm viewing it. Now I need the current going to the right out of that V sub A horizontally. And now I'm not worrying so much about this voltage between the R sub 2 resistor and the inductor. Let me just lump these series impedances as to one impedance and just worry about that whole drop. That's still V sub A. This drop, V sub A, is the same as the drop across R sub 2 and SL. So that now I have V sub A all over R sub 2 plus SL, and that's equal to 0. There's now one equation in the one unknown, V sub A. And I can solve this for V sub A. And it will be a function of the input X. Oh, I didn't want V sub A. Well, I do. How do I use V sub A to get my result? I need Y, don't I? But that's just the voltage divider, isn't it? If I can find V sub A, then Y, the output, is now going to be R sub 2 over R sub 2 plus SL. Now I simply need to find V sub A in terms of capital X. And that's just some algebra. But let me collect that. Let's just see if that works. So we already have the answer in the back of the book, don't we? We just derived it the brute force way. We had our calculator. So we now have 1 over S squared plus 2S plus 2. That's the answer in the back. Now we want to check. We're doing it another way. We're saying, do I really believe this transfer function? Let's see if we do. If we now go back to this equation for V sub A, I now have 1 over R1 plus SC plus 1 over R sub 2 plus SL V sub A, and all of that is equal to 1 over R sub 1. going to say SR1C times SL plus R sub 2 plus SL plus R1 plus R sub 2. I'm just rearranging some of those, but hopefully I'm not changing anything. And that's now times X. I really wanted Y, didn't I? But Y is just a couple lines up. That was just 1 over this R2 plus SL times V sub A. With that R sub 2 still there, I haven't yet made it 1. So I have R sub 2 divided by essentially this expression, meaning Y of S is now equal to R sub 2 over S R1C SL plus R sub 2 plus SL plus R1 plus R sub 2 times X of S. And if I replace my R's, L's, and C's with 1s, I better come up with the same answer, because this is the same transfer function. This is the same system. If I make R's 1, C's 1, and L's 1, I end up with S squared. I end up with S plus now Y of S is equal to 1 over. So this is with R1, R2 equal to 1, C equal to 1, and L equal to 1. S squared plus 2S plus 2 that's now my G of S. Questions on that? What is this system going to do? What did we say at the very beginning of class? What does this electrical circuit look like effectively? A low-pass filter. So now you could sketch the Bode plot of that if you wanted to. You might want to know, where are these? If I find values of S that cause this denominator to vanish, what are those called? Do you remember what we called those? Those are poles, aren't they? The zeros are the values of S that cause the numerator to vanish, the finite values of S that cause the numerator to vanish. So if we wanted to know what the poles are, that gives us the natural behavior of this circuit. They're the values of S that satisfy this. And if, I don't know why I'm playing with death here, but we could try to do that here, couldn't we? We could go over here and we could open up our little manual of commands and we could say, find the complex zeros expression. And now I want to do, because I know that that particular expression, S squared plus 2S plus 2, if I use the quadratic formula, it's going to give me complex roots. It's not, it doesn't factor with real roots. Now I can say, oh, what did I have? I had X squared plus 2X plus 2, and I could say that's going to be as a function of X. And now those are my pole locations, -1 plus and minus J 1. Those are now my poles, meaning I now have poles there. Or I could rewrite that in the form that I like to write it. I like to write this as S plus 1 squared plus 1 squared. which really is saying that I have s plus the real part squared plus the imaginary part squared. In this picture, in the s-plane, where I might have the real part over here at minus sigma, and maybe my imaginary part, j omega sub d, and its twin, minus j omega sub d, I would now have poles here and here. And in our case, this sigma was 1, and this omega sub d was 1, meaning this distance, vertical distance, was the same as the horizontal distance. And it's now at an angle of 45 degrees relative to the negative left half plane. And they were negative. It's in the left side of the complex S-plane. That's a good location for those pole values. And you can show that if I have some denominator polynomial that's factored like this, that will lead to, if you replaced s with minus sigma plus j omega sub d, that will vanish. And if you let s equal to minus sigma minus j omega sub d, that will also cause that expression to be true, or for it to equal 0. So those immediately tells me where those poles are located when they're complex conjugate pole pairs. Now, how did we start this lecture? We started this lecture saying, given an x, what's y? What if I said, let's just look at something pretty easy. Let's just say, let's let x of t equal 2. And I could say that's either 2 for t greater than or equal to 0. You're going to see that written as 2 times u of t, where this u of t is acting like a switch. That's the unit step. It's the same concept or idea. Now you replace that circuit with this picture, where your circuit is this g of s. This is just a system. And g of s we've now found. That's 1 over s squared plus 2s plus 2. And we know that has poles at minus 1 plus and minus j1. That actually means we have exponentially damped sines and cosines in our natural behavior. So if I walked up and kicked that circuit, I don't kick it, what do? I inject it with an impulse, maybe. I said we were trying to connect this with what you already know. What's capital X of S? What's the Laplace transform of a unit step? So we're scaling whatever u is, whatever u's Laplace transform is, we're scaling it by 2. But what's the Laplace transform of a unit step? 1 over s, isn't it? So this is now 2 over s. We now know what capital Y of s is. That's now g of s times x of s. G of s was 1 over s squared plus 2s plus 2. X of s was 2 over s. Now what do? We want the structure of little y of t. I just need to know what pieces make up little y of t. What component pieces? And that could be constant piece, it could be sinusoidal piece, it could be exponentially damped pieces, it could be exponentially damped sines, exponentially damped cosines. How do we find that out? We need to know where our poles are, right? And do a partial fraction expansion on this capital Y of S. That's how we find the structure. And we know where these poles are. Where's this pole? What value of S causes that polynomial to vanish? 0. That one's so easy it's hard, right? So we have a pole at the origin. We have a pole at S equals 0. Where are our other poles? We have 2 poles because it's second order due to the system itself. And we just found where those poles were. -1 plus and minus J1. That now says that we have the following structure, partial fraction structure for Y of S. We have a constant piece due to the pole at the origin. And we have another piece, let me call it B, that will be an exponentially damped cosine sine. Maybe that was a poor choice of R's, L's, and C's because this 1 in the S plus 1, that's going to be in the e to the minus piece. This one, this damped frequency, is going to be in the cosine and sine frequency piece. Meaning, this now says that I can immediately write down, without calculating A, B, don't need you to numerically find A, B, and C. I figure given a calculator or given enough time, you can do that. That's not what I'm going to ask you at that point. Questions on that? What if we tried to do this in the time domain? Wow, what in the world? He went from B to 1 to 10. What kind of counting is he doing? want to concentrate on these variables that have this first derivative piece. Meaning, if somebody says, oh, what are your key variables in this circuit? Then you would go, Eli the Iceman, Eli the Iceman, Eli the Iceman. Oh, yeah. Voltage across the capacitor and inductor current. So if I can write my equations in terms of inductor currents and capacitor voltages, that'll probably make for a cleaner set of equations. And these we will call state variables in chapter 10. Let's now see if we can write some equations for this circuit in terms of inductor current and capacitor voltage. Meaning I would now probably go up here and I would say, okay, I want to write in terms of this and this. And now you're going to think, well, where in the world he's been in the ice too long, right? Once I start writing this. But I might start writing a KVL equation around the left mesh. And that would look like minus x of t plus r1, oh, let me just call that I sub 1. I don't know what it is yet. Plus, oh, that's just v sub c of t. So from mesh 1, I sub 1, I can write in terms of this capacitor voltage and this inductor current. What's the current through this capacitor? Well, in terms of this guy, this capacitor voltage, it's ice, isn't it? This current